All right, so number 31, we're solving an equation again. We have log base 7 of 49 equals 2x plus 7. We want to start out by changing it to exponential form. We'll put our base with our exponent. So 7 raised to the 2x plus 7 equals 49. We see that we can use 7 as a common base. We'll rewrite 49 as 7 squared. So we'll have 7 raised to the 2x plus 7 equals 7 squared. Now we have the same bases. We can get rid of those bases, set the exponents equal to each other. So we'll have 2x plus 7 equals 2, and we can finish solving from there. Subtract 7, divide by 2, we get x equals negative 5 over 2. So now moving on to problem number 32, it says e to the 2x equals 5. So this time we have an exponential equation, and up until this point we have been changing the rewriting the exponential equation so that the bases are the same. However, we have a base of e and we have a base of 5, so we cannot rewrite the bases so that they are the same. So when we cannot rewrite the bases so that they are the same, we're going to take the logarithm of both sides. In this case, the base is e, so we can just take the natural log of both sides. Typically, we can use either ln, which is the natural log, or we can just use log, which is the common log, which is the log of base 10. So we're going to take the log of both sides whenever we cannot rewrite the exponential equation using the same base. So we put ln on both sides. We're really just attaching ln to both sides of the equation. And we see that on the left side of the equation, we can simplify. So we'll simplify the left-hand side using the properties of logarithm. So we'll basically say, okay, we have ln e, which is going to cancel each other out. So we're going to be left with 2x equals ln 5. And we can finish solving from there. We're going to divide both sides by 2. And for problems like 32 through number 36, they want us to leave our answers in the exact form. They don't want us to estimate, so we'll leave our answer as ln 5 over 2. Number 33, we have another exponential equation where we cannot write the bases as a common base, so we'll take the natural log of both sides once again. We'll have ln e raised to the 3x plus 4 equals ln 15. We'll simplify this left-hand side over here using log properties. Remember, whenever you have the same base as well as the argument, those will cancel out, and we have this exponent that we're left over here. We'll have 3x plus 4 equals ln 15, and we can finish solving it from there. We treat ln 15 like it's any other number because it actually is just a constant. It's some irrational number where we'll get a decimal, which is why we leave it in exact form when we're working through the problem. So from here, we'll subtract 4. We'll have ln 15 minus 4, and then we can just divide by 3. So we'll have x equals ln 15 minus 4 over 3. All right, number 34, we have a log equation. This time we need to change it to exponential form. So we'll end up with 3 squared equals x squared plus 8. And we want to simplify this exponent over here. So we'll have 9 equals x squared plus 8. We want to get the x by itself in this case. So we can subtract 8 from both sides. We'll have 1 equals x squared. Very obviously so, we see we will end up with the square root of 1 equals the square root of x squared. So x equals 1 or negative 1. In this case, we can keep our negative answer because it is not going to make our argument be equal to or less than 0. We can plug in negative 1. We'll get 1 plus 8 either way. So we can keep our negative in this case. Remember, you just always want to go back when you get those negative answers, especially just make sure that it is still included in the domain before we include it as a part of our solution. Number 35, we have log base 4 of 64 raised to the x power equals negative 3. So it's a couple different ways we can go about this problem, but here we want to change it to its exponential form and then solve the exponential equation from there. So we'll put 4 raised to the negative third power equals 64 raised to the x power, And then from here we can see that 4 can be used as a common base. We'll rewrite 64 and change that to 4 raised to it would be 4 raised to the third power. However, you have this x here, so it's going to be 4 raised to the 3x power. So now the bases are the same. We can drop those bases. We'll have negative 3 equals 3 times x, and then we can divide both sides by 3. We'll have negative 1 equals x, and we have a negative number, but if we go back and plug it in, we'll simply still get a positive number for our argument, so that is not a restrictive value. 36. So now we have an exponential equation, but before we begin manipulating the equation any further, we want to have our exponential expression, which is 10 raised to the 4 minus x by itself. So first we're going to divide this 2 away over here to the right side so that we have 10 raised to the 4 minus x by itself. So that way when we take the log of both sides, we're only taking the logarithm of this exponential equation on the left. So we'll take the log of both sides here. So now now you see this time we're using the common logs. So remember, when you see log and there's no base written, that means that the base is 10. That's what the common log is, log of base 10. So we have log being taken of both sides, and here in this case we have base 10 as well as an argument being 10, so they will cancel each other out. So now we have log base 10 of 10, they cancel each other out. We're left with 4 minus x on the left side, and we just leave it as log of 13 over 2 on the right side. And from here we can finish solving it. We would subtract 4 from both sides, and then we can divide everything by negative 1. So we'll end up with 4 minus log 13 over 2 equals x. All right, so for number 37, this time they give us a function and they ask us about some properties of the function. So it says, what is the domain of our function? So for the logarithmic functions, we go to our argument here. We set it greater than 0, so we have 2x plus 2 is greater than 0 to find our domain. We end up with x is greater than negative 1. Interval notation that's going to take us from negative 1 to positive infinity. For part B, it says what is g of 1 and what point is on the graph when they're asking us about the function value when x is equal to 1. So we substitute 1 into the equation. So we have log base 2 of 2 times 1 plus 2 minus 3. So then we'll have log base 2 of 4 minus 3. And we can evaluate this logarithmic expression. Remember, our logs ask us questions. It's saying 2 raised to what power equals 4? And that is 2. 2 raised to the second power equals 4. So log base 2 of 4 equals 2. So we evaluate the log and we rewrite the problem to finish solving it. So we have 2 minus 3, which is equal to negative 1. So when we plug 1 into the function, we get g of 1 equals negative 1. And the point that's going to be on the graph is going to be 1, comma, negative 1. For part C, it says if g of x is equal to 1, then what is x equal? So this time we're plugging in 1 for g of x. So we're setting our equation now. We're setting the function equal to 1. So first, to solve this now, we're solving for x. We want to have the logarithmic expression isolated. So we're going to add 3 to both sides of the equation first. 1 plus 3 gives us 4. So now we have it where 4 is equal to this logarithmic expression over here. So now we can change it to exponential form. Everything else has been moved away from the logarithm, so we can simply manipulate it into writing it as an exponential equation. So now we'll take the base, which is 2, raise it to the 4th power. 2 raised to the 4th power is now going to equal our argument, which is 2x plus 2, and we can simplify the exponential expression and finish solving. 2 raised to the 4th power is 16. 16 now equals 2x plus 2. We subtract 2, divide by 2, and then we get 7 equals x. 7 is our x coordinate. They gave us 1 for our y coordinate, so now the point is 7, comma 1. So now for part D, it's asking us what is the zero of the function. And remember, the zeros of the function are points on the graph where y is equal to 0. So to solve this one, we're going to set the function equal to 0. We'll plug in 0 for g of x and solve for x. And then once again, we want to get the log expression isolated by itself. So we'll add 3 to both sides. We'll have 3 equals log base 2 of 2x plus 2. And we need to change it to its exponential form. So we'll have 2 raised to the third power equals 2x plus 2. 2 raised to the third power simplifies to being 8. So we have 8 equals 2x plus 2. We subtract 2 again, we divide by 2 again, and this time we're left with x being equal to 3. Now moving to 38, it's asking us about a scenario, an application problem. It gives us this function here, and it asks us some questions about this function. So for part A, it's saying what is the pH of the solution when H plus is 0.1. So we're going to plug in 0.1 for H plus, and we'll evaluate it. For part B, it's a very similar situation. This time they give us 0.01 to plug in and evaluate, and then they give us 0.001 to plug in and we evaluate it, and these are the values that we get for part A, B, and C. Part D is saying what is happening to pH as the hydrogen ion concentration is decreasing, and we see as the numbers that we're plugging in for our hydrogen ion here that's positively charged is decreased. Those values are decreasing. However, the outputs, the pH values, are increasing. So for part D, we'll choose the first answer choice, which says the pH is increasing. Now, for part E, it's saying determine the hydrogen ion concentration that has a pH of 3.4. So this time we're plugging in 3.4 for pH, and then we're solving for the hydrogen ion. So in order to solve it, we need our logarithmic expression to be isolated first. We'll divide everything by -1. We'll have -3.4 equals log base 10 of the hydrogen ion, and we're going to change that to the exponential form, So we'll have 2 raised to the -3.4 equals the value we're looking for. We simplified that, 10 raised to the -3.4, we get this long decimal, and it tells us to round it, so we round it as we're directed, and this is what our final answer is. For part F, it says determine the hydrogen ion concentration when the pH is 7.4. So we go through a similar process. We plug in 7.4 for pH, and then we are going to change it to exponential, and we are going to simplify it this time. Even if you type it in your calculator, most calculators, it'll just spit it out in scientific notation, and this is what we are going to be left with, 3.981 times 10 to the -8. So that is our first answer choice for this one, and we are done.